This video is on the effect of the Earth's rotation. This is known as the Coriolis effect. Coriolis deflects objects like large-scale air and water masses from their direction of travel, deflects them to the right in the northern hemisphere and to the left in the southern hemisphere. It's a result of the Earth's rotation, or the fact that we are on a rotating Earth. We have a rotating frame of reference. Good way of visualizing the effect of a rotating frame of reference is to consider a ball being thrown from the center of a merry-go-round to a target that's off the merry-go-round. So here we have center of the merry-go-round, then these white dots are the ball traveling away towards the target here. In this case, our merry-go-round is rotating counterclockwise, and we have an observer on the merry-go-round who is also rotating counterclockwise. T0, T1, etc. corresponds to a time where the ball will be at that time and where the observer will be at that time. At T0, the ball is thrown in a direction such that the observer will see it coming more or less straight towards them. And then as time progresses, the ball travels further and further, and the observer gets further around the circle. So from the observer's point of view, they're going to see that the ball doesn't travel in a straight line like it does when we're looking down on the merry-go-round. They're actually going to see that it curves. As they move around relative to the ball is going to look like it curves. So as time progresses, the observer is seeing the ball deflected to the right as it travels. So direction of motion is in this direction, T0 to T1 to T2. So this is time, and it is being deflected to the right as you follow that arrow around. So on Earth, if you look down on the North Pole, the Earth will be rotating counterclockwise. So this is the scenario that we just looked at here, with the deflection along the direction of travel being to the right. If we were to look up on the South Pole, the Earth rotates the other way. The Earth rotates clockwise. So now we have the same scenario, except our merry-go-round is going in the other direction. The ball is being thrown to a target, and the observer is going around. So as the ball is thrown, the observer is seeing it curl away, this time in the direction of propagation. The ball is curving to the left, or being deflected to the left in the observer's frame of reference. Like before, the ball itself is not curving. It's the apparent motion in the observer's frame of reference. So taking this up to the Earth, let's do a thought experiment. So Quito in Ecuador is right on the equator, and it is directly south of Buffalo, New York. The Earth is fattest at the equator, so if we were to take a disk through the latitude of the equator, it would have a larger diameter than any other disk we did at a constant latitude. So we have our disk here at the equator, and then here is a disk drawn for the latitude of Buffalo, New York. So you can see that the diameter of the equator disk here is larger than the diameter of the Buffalo disk up here. So the entire Earth is rotating once every 24 hours, so once a day. And that means that any point on the equator, that larger disk has further to travel. So any point on the equator is going to be traveling at around 1,600 kilometers an hour. As the disks get smaller as we go poleward from the equator, so here there's a disk through 30 degrees latitude north, and any point on that disk will travel at 1,400 kilometers an hour. At 60 degrees north, the disk through that latitude is smaller again, and any point on that disk will travel at 800 kilometers an hour. And when we get to the North Pole or the South Pole, the disk is 0 in diameter. So in 24 hours, if you're standing exactly on the North Pole, take you 24 hours just to turn around 360 degrees. So how does this play into our thought experiment? Well, let's imagine that you were firing a cannonball or a big paper dart or something up from Quito, firing it directly north, planning to get it to Buffalo, New York. If we start at Quito, then when you launch your cannonball, it's already got a 1600 kilometer an hour component to the east because of the Earth's rotation. So as soon as the cannonball leaves direct contact with the Earth and into the atmosphere, then it's no longer got that velocity component directly acting on it. Then as it travels north, it's going over sections of the Earth that aren't traveling as fast. So any point, on this 30-degree line is traveling 200 kilometers an hour slower than the equator where it left. So it's actually rushing ahead of these points, and so it will land in the Atlantic because effectively it has overshot Buffalo because of its initial eastward component. So in the direction of travel, looking north, it will look like the cannonball has curved to the right. So that's the Coriolis effect. So what's happening if we went the other direction? Buffalo replied with a cannonball or big paper dart. So now it's got a lower eastward component when it's launched. So it's up here somewhere. And then it's flying down, not directly getting any friction from the Earth. And so it's coming over, but now it's heading towards an area where any point on the globe is moving faster. So in effect, as it's coming down, the globe is running faster underneath it than it's going. So it's going to curve, and in this case, going to land in the Pacific Ocean. So again, in the direction of travel, so from north to south, it's curving to the right. This is all northern hemisphere. So in summary, the Coriolis effect is a direct consequence of the Earth's rotation and the fact that we are on the Earth making these observations. In the northern hemisphere, it deflects objects to the right, and in the southern hemisphere, it deflects them to the left when you're looking along the direction of travel. The magnitude of the deflections increases as you get closer to the poles. The Coriolis effect is actually zero at the equator, which makes sense because it's switching sign at the equator from being right to left, so it has to go through zero at that point. The Coriolis effect acts over large scales. So in our case, large air or water masses. So we're doing this here in context of the atmosphere, but in the next section, we'll see that Coriolis has a huge effect on ocean circulation as well. In order for the Coriolis effect to act on an object, it can't be in direct contact with the solid Earth. So you would never get Coriolis effect on your car because your tires have too much friction. Also, Coriolis needs to be over some significant distance. So you can barely detect the Coriolis force in the trajectory of a long-range bullet, but you can't detect it in things like the rotation of toilets. The rotation in a toilet bowl is a direct consequence of the way the water was fed in there. Also, if you look online, you'll be able to find videos of people pretending that, as they take a couple of steps across the equator, that the rotation in a fish tank changes. This is wrong. It's a sleight of hand for a couple of reasons. One, as I just said, Coriolis acts over large scales, not fish tank type scales. Two, the Coriolis is zero at the equator. So what's happening is, as they do it, they give the fish tank a very slight rotation in either direction to make the illusion that the rotation has changed. So an important thing to remember from this video is northern hemisphere deflects to the right, southern hemisphere deflects to the left.